In this video, we're going to do some extra examples using composite functions, so composing two functions together. So just remember the notation and the definition, I guess. So when you compose two functions, we use this little circle, and you read it as composed with. So this is f composed with g of x. Okay, so that's the function. And the way that we compute that is f goes on the outside, and then it's g of x on the inside. So it's f of, okay, not multiplied, but of g of x. So that means it's function f evaluated at g of x. So everywhere you see x in the equation for f of x, you're going to insert g of x. Okay, so that's what that means. So let's do an example here. So we have f of x is 3x minus 4. And g of x is x squared minus 1. And in part b here, we want g composed with f of negative 2. So that's actually g of f of negative 2. So it might be useful to figure out what is f of negative 2. So let's do this on the side. So that's when I plug in negative 2 into f. So that's going to be 3 times negative 2 minus 4. So that's negative 6 minus 4, so it's negative 10. Okay, so that means that g of f of negative 2 is actually g of negative 10. Oops. Okay, so everywhere I see an x in g, I want to put in negative 10. Maybe I should just highlight. So f of negative 2 is negative 10. Which we found in the blue part. So now I want g of negative 10, so that's going to be negative 10 squared minus 1. So it's going to be 100 minus 1, or 99. Okay, so that's our answer. So now notice here we got a number, whereas in part A we got a function of x. That's because there's an x here, but here I'm evaluating at a number. So you could have, if you wanted, computed g composed with f of x first. So that's g of f of x. So that's everywhere I see x and g, I'm going to put in f of x. So that would be 3x minus 4 all squared minus 1. And obviously you could simplify this, but if I now plug in x equals negative 2, I would also get 99. Okay, so this is the function in terms of x, and this is it evaluated at x equals negative 2. Okay, so it works the same way. Because we just wanted it at a number here, I just did it, used the number right away, which is a bit easier to do generally, but you could have found the equation in terms of x and then plugged in your number as well. Okay, so let's try another one. So here's one for the domain that is actually a little bit harder than the one that we did. Okay, so it's s composed with r of t. So we're going to find that function first. So it's s of r of t. And r of t is a polynomial. So it's s of 1 minus 2t plus t squared. So everywhere I see t in s, I actually want to put in this whole expression here. So that's going to be 3 over 1 minus 2t plus t squared. Okay, and then minus 1. So I could actually simplify this. The 1's are going to cancel. So it's going to be 3 over t squared minus 2t. Okay, which you could factor as well. Okay, but that's what it looks like. Now you could compute the domain from this, because we computed this composite function, you could compute the domain from here. But let's try and use these domain rules, okay, to compute it, just to make sure that we know how to do that. Okay, so for the domain, so we want the t values to be in the domain of R, okay, which is all real numbers. Okay, so we have everything so far. But now we also need r of t to be in the domain of S. Okay, so what that means, so S has domain, we already have it up above, t not equal to 1. So what we need to do is we need r of t not equal to 1, because that's going to ensure that r of t is in our domain. Okay, so that means that, I find r again, so I need 1 minus 2t plus t squared not equal to 1, which is, if I subtract the 1 over, that means t squared minus 2t is not equal to 0. And then if I factor out a t, I get t times t minus 2 all squared is not equal to 0, which means that I can't have t equals 0 or t equals 2. Okay, so this is the domain of S composed with R. Okay, and you would get the same thing, as you can probably see, from the computed version, right? So if I factor, this is t times t minus 2. So see, we get this denominator here. Okay, so we're doing the same thing as we would do if we use the function. Now I just want to make this slightly better. So it's S composed with R. Okay, let's try another one. So here I have a table and I want f of g of 3. Okay, so the first thing I want to do is find g of 3. Okay, so what that means is it's the y value when x equals 3. So I look at x equals 3, and then I want to find its y value. So for g, that's 1. Okay, so this is actually f of the number 1. Okay, now that number 1, which used to be a y value, is now my new x value. So now I go back to my table and I look at, okay, when x is 1, what's f of x? Well, it's 2. So I want that one, and that's the answer here. So this whole thing is equal to 2. Okay, so this part here is the y value when x equals 3. Okay, so that's the 1, but then it becomes my new x value. So the 2 is the y value of f, maybe I should write here, of g, but here it's when x equals 1. So the old y value is my new x value. That's how the composition works. Okay, now for this one, we showed half of it, so we wanted to show the other half. So I want to show that g composed with f of x is also equal to x. Okay, so that's g of f of x. So that's g of 3x minus 9. So I use the g equation, but everywhere I see x, I instead put in 3x minus 9. So I have 1/3 times x, so that therefore it's times 3x minus 9. And then plus 3. Now this 1/3 has to factor through. So I get 1/3 times 3x is just x, minus 9 times 1/3 is 3. So I have x minus 3 plus 3. Those go away, and I get just x. So again, here we got g composed with f of x also equal to x, which is what we wanted. Now remember, I said this doesn't always happen. Okay, these are special functions that we're going to talk about in the next section, and that's why this property works for these two. Okay, but in general, with any two functions, it doesn't always work like that, as we've seen. Okay, last example here. So I have a function, h of x, that looks like it could be a composition of functions. Okay, so we want to figure out what the f and the g would be that would give this function when I compose them together. So again, I'm going to do a few different ones. Okay, so answer 1 is going to be the best one in terms of calculus. So we have our our f of x and our g of x. So remember, g of x is the inner function and f of x is the outer function. So it's better to find the inner one first. So for this first answer, I'm going to use the entire, so it looks like I have something inside of a cube root. Okay, so that inside bit I'm going to use as g of x. Okay, so that's my inside function. Now, if I use that as g of x, when I do f of g of x, I'm going to be replacing all of my x's with g of x's. So I want to do that in reverse now. So where I have g of x, which I do here, okay, that's my whole g of x. What I want to do is replace that with x. So my f of x is going to be the cube root of just x. Because then when I do the composition, it's going to be f of 4x squared minus 1. So I'm going to be replacing the x here with that whole thing. And that's going to give me my h of x back. Okay, so that is h of x, which is what we wanted. Okay, now another different way you could do this. So let's again f of x and g of x. I'm not going to expand it out this time, but instead I could take g of x to be just the 4x squared. Okay, and then what f is going to look like is it's going to be the cube root of x minus 1. Okay, so for this one, this is the part that I took. Okay, that's my g of x, so that's where I want to replace that bit with just x. Okay, or we could have another variation. Maybe we let g of x just be x squared. Okay, so then the x squared I see is just right here. I can't really see that color over the green, but so then f of x would be the cube root of 4x minus 1. Okay, so when I replace this x with x squared, I'm going to get the h of x back. Okay, so that's another one. In fact, there's more. Okay, now those ones are sort of the most obvious. So this one is a bit weird. Okay, but then there's lots of different ways to do this. Oops. So here, maybe I use g of x, so this is a weird one, but I could do 2x, because f of x I could write as the cube root of 2x all squared minus 1. Okay, so then what I'm doing here is replacing that bit. So then my f of x would look like the cube root of x squared minus 1. Okay, so that's even yet another, and I'm sure there's more. Okay, but this answer 1 is the best one in terms of calculus, and it's the easiest one to come up with as well, hopefully. What you don't want to do is let g of x be x and f of x be the actual function. Okay, obviously that works, but it kind of defeats the purpose as writing it as a composite function. Okay, which is useful and is something that we want to do. So those are a bunch of different examples of how you might do that. All of them are correct. Okay, so there's lots of different functions that could be used to compose to make h of x here.